Your communication is breaking up. Kingsley, we are going to start where we left off the other day. Um, yes. I don't recollect very much whether we did gases the last time or not. Who remember that we did gases or we didn't do gases? Who remember? Nobody remembers. Who remember whether we did gases or not last week, last 2 weeks or so? Nobody can hear me. Then I have to log off because if nobody can hear me, then I will log off.
Please, we can hear you.
But I'm asking whether this we did gases last time or not. All right, if you don't remember that, let's learn the gases, okay? Um, we are going to do that kinetic theory of gases, and then we do some laws involved with gases. All right. Kinetic theory of gases describes the state of matter as composed of tiny particles in constant motion with a lot of distances between the particles. Right? It's based on the following statement. Um, gases consist of tiny particles of matter that are in constant motion. Right? Gas has tiny particles and they are in constant motion. Gas particles are constantly colliding with each other and they weigh in the walls of the container. And this collision are elastic. When we say it's elastic, that means there's no net loss of energy from the collision. All right. And then gas particles are separated by large distances, with the size of a gas particle tiny compared to the distances that separate them. So this is the number three of the kinetic theory of gases. And then there are no interactive forces. All right. That means there's no attraction or repulsion between the particles of a gas. And the average speed of a gas particles depends on the temperature of the gas. This is the kinetic theory of gases. Um, and that's ideal gas. So if you see, this is a container, and then the particles are inside the container, they're bombarding on the walls of container, and also they are bombarding on themselves. Okay. So this is a kinetic theory of gases. All right, most of the gas is empty space. So that means it makes the density of a gas very small. All right, because a gas has a low density because and it can contract and it can expand under appropriate influences, especially when the changes of the when the pressure of it changes or the temperature of it changes, right, or both. Then it can either contract or it can expand. Alright. So gas particles are in constant motion. So and it means that two or more gas will always mix. as the particles from the individual gases move and collide with each other. An ideal gas is a gas that exactly follows the statement of the kinetic theory. All right. So we have ideal gas, we have real gases. So ideal gases they follow the kinetic theory of uh, gases, like what I just said. They bombard with each other. The bombardment is elastic. All right. There's no net loss of energy. They create pressure on the walls of the container that they bombard, and then and they collide with each other. All right. And they can expand, they can contract, and that's gases. So we have ideal gas, we have rare gas. Ideal rare gas does not follow the ideal gas, and many gases deviate from slightly from the agreeing perfectly with the kinetic theory of gases. All right, and most gases adhere to the statement so well that the kinetic theory of gas is well accepted by the scientific community. Scientific community agree to use ideal gases, but some instances we use rare gas. We use Van der Waals equation, barrier equation, all those kind of equation that we use to deal with rare gases. All right. The gas particles in constant motion, they bombard on the walls of the container they are in. All right. They bombard on the walls of the container. So that by so doing they create pressure. All right. So we have pressure. Gas has pressure. All right. And the accumulation of all the forces distributed over the area of the walls of the container causes pressure. Uh, so it can mix gases together. And then when you mix them together, then they'll be creating pressure because the particles are hitting the walls of the container. So the area that the particles are hitting, all right, and then you have the force that they're using to hit on the walls of the container, creates a pressure. All right. So the pressure is force divided by the unit area of the gas. All right. So the pressure of the atmosphere is about 14.7 pounds of force per every square inch of surface area. And so which is 14.7 pounds per square inches. And pressure has varieties of units. Uh, so the former unit that we use SI approved unit is the Pascal. We use Pascal as the unit. But then beside Pascal, there are other units also. Atmosphere, millimeters of mercury, torr, and so forth and so forth. All right. And these are the conversion factors. All right. One atmosphere equal to 760 millimeters of mercury, which is equal to 760 torr, which is also equal to 101 325 Pascal. All right. So given a 1 unit of pressure, you can convert it to another unit. But these are the conversion factors of pressure. All right. As much as temperature has its different conversion factors, and we have Rankine, uh, we have Celsius, we have Fahrenheit, we have Kelvin. We have different type of temperature unit. Pressure to have different type of pressure units. All right. So then all I need to do is just get the conversion factor and get it one pressure I can use the other one. So if you are using the SI unit, then it has to be Pascal. I know and the Pascal is 1 Newton per meter square. Newton is also SI unit for force. All right. And then the meters is the area is meter square. Distance is meters. All right. And raise this to the power. All right. So 1 Newton per meter square. For more reliable and common units is millimeters of mercury, which is the amount of pressure exerted by a column of mercury exactly 1 millimeter high. So that's why we say millimeter of mercury. That's our definition of millimeter of mercury. All right. So given this example, Let's go through this example. The atmosphere on the Mars is largely carbon dioxide at a pressure of 6.01 millimeters of mercury. What is this pressure in atmosphere? All right, so we're coming over here, right? You just take the millimeters of mercury, multiply by the conversion factor. One atmosphere is 716 millimeters of mercury, which gives you 0.00791 atmosphere. All right, and that's it. Um, you just have the conversion factors. Then there are some laws that involve with the pressure and also with the gases. We have the Boyle's law, we have Charles' law, we have Gay-Lussac's law, we have Avogadro's law. All those laws governing the ideal gases. All right. So when you are dealing with ideal gases, depending on what you have and when you are, you've been asked to deal, you can use one, law to find whatever you are looking for. These are the proven laws. People have used it and it's been working for years. So then we can also use it to do our work. All right. So the Boyle's law deals with pressure and volume, right? So when you have a amount of gas, and then once its pressure is increased, then its volume decreases. And then when its volume increases, pressure decreases. All right, so that's Boyle's law, and it's constant. So given the same amount of gas at the same temperature, then pressure times the volume becomes a constant. Given the same amount of pressure and the same amount of volume and the same amount of moles, the number of moles, the maybe quantity of it, right? The moles are converted into mass. So we can go over them, how moles are converted to and mass and stuff like that. All right. So given amount of moles and given amount of temperature being constant, then PV P1 V1 equals to P2 V2. Then given a problem with this, we can just use it to solve the problem, right? So P1 times V1 equals to P2 times V2 becomes a constant. This is a Boyle's law, right? Boyle's law. So we can do problems with it, and then we can also. So this is the thing, this is a graph, of it. Here you see this is a PV diagram, pressure and volume diagram. The volume is changing, the pressure is changing. All right, this is a negative curve. The pressure is on an abscissa, and then the volume is ordinate. All right, and as volume is decreasing, pressure is increasing. As pressure is decreasing, volume is increasing. And here you see these test tubes. All right, V is large, P is small. Here V is small, P is large. All right, so they are inversely proportional. Inversely proportional. Okay, so using that, we can use that to do an example. A sample of gas has initial pressure of 2.44 atmosphere and initial volume of 4.01 liters. This pressure changes to 1.93 atmosphere. What is the new volume, temperature, and amount are kept constant? All right. So now we have P1 V1 equals to P2 V2. We know them, so we can just put them together and then we can solve the problem. All right. So um so 2.44 atmosphere times 4.01 liters equals 1.93 atmosphere times the volume V2. And let's put them together. This is very simple mathematics that everybody who's in university is supposed to be doing. Just divide both sides by 1.93 and V2 gives you 5.07 liters. Then, this is just a simple, then we come to Charles' law. If the amount of a gas and its pressure are kept constant, then changing the temperature changes the volume. All right. This for the Boyle's law, you keep the number of moles and the temperature constant. For Charles' law, all right, you keep the pressure and the number of moles constant. The V1 over T1 equals to V2 over T2. The volumes, these are the directly proportional. Volume is directly proportional to temperature. All right. Volume is directly proportional. For the Boyle's law, the pressure is inversely proportional to the volume. But for Charles' law, the volume is directly proportional to the temperature. So V over T equals to constant. As temperature increases, volume increases. As temperature decreases, now volume decreases. These two characteristics are directly related. And this is the mathematical relation between volume and temperature should be possible. All right. So the volume of a gas related to absolute temperature. Absolute temperature. Hence, V over T equals to constant. So suppose the initial conditions V1 and T1 have a certain value, and the value must be the same when the condition of the gas has changed to some new conditions V2 and T2, as long as pressure and the amount of the gas remain constant. Thus, V1 over T1 equals to V2 over T2 at constant pressure and number of moles. All right, that's Charles' law. So in this ways, when volume is increasing, temperature is increasing. When temperature is decreasing, volume is decreasing. All right, this is Charles' law. All right, this is temperature and volume graph. This is a positive graph. All right. So using that, let's use that to do some example. A sample of gas has its initial volume of 34.8 milliliters, and initial temperature of 315 Kelvin. What is the new volume if the temperature is increased to 559 Kelvin? Assume constant pressure and amount of the gas. I leave this for you. Everybody get to work. I'm giving you some time to do some work and give me listen. Everybody get to work.
Hello, sir.
Yes,
Please,
yes, Patrick.
my network was jamming, so I didn't hear what you just said, the last word.
I was saying that this is the work that you guys have to do now. Let's see who's come up with the correct answer.
Oh, okay. Thank you, sir.
Sure.
Hello, sir. Hello, sir.
Yeah, Ray. Yeah, Ray.
Yeah, so the new volume becomes 61.8 milliliters.
Okay, let's see. Has everybody finished?
Yes, sir.
All right, let's see. Part is also finished. Yeah, 61.8 milliliters. You're right. That's right. If you are done it that, if you couldn't do it, you ask yourself how it's done. All right. You see that, but this one is V1 over T1 is equals to V2 over T2. Changing and making it T1 over V1 equals T2 over T2 give you the same answer. So this one is just a simple but knowing when the temperature and knowing that the temperature or knowing that the pressure and the number of moles are kept constant. Uh, Now we have Gay-Lussac's law. Gay-Lussac's law. All right. It relates pressure with absolute temperature. In terms of two sets of data, right? Gay-Lussac's law is P1 over T1 equals to P2 over T2. Right, this is when the number of moles and the volume are kept constant. Uh, in high school, mostly we were taught the Charles law and Boyle's law, but we extend it more, right, to Gay-Lussac's law and Avogadro's law, you know, and some of them because this one is not really it's general chemistry, it's not physical chemistry. That I would have been doing, real gases too, all right. But um, this one is Gay-Lussac's law, P1 over T1 equals P2 over T2 at constant volume and number of moles, all right. And then this one is Avogadro's law, right? Don't forget, Gay-Lussac's law is when you have to know when this is kept constant. There are some problems when you are given some problems, you wouldn't know, and you will not be explicitly told that these are constant. But giving the information in the problem will tell you that, oh, okay, I believe these are constant. All right. For Gay-Lussac's law, the number of moles and then the volume are the one that are kept constant. For Charles' law, it is the pressure and then the number of moles that are kept constant. For Boyle's law, is the temperature and number of moles are constant. So you see, mostly the number of moles are kept constant. How much we have are kept constant. But when it comes to Avogadro's law, then both the temperature and pressure are the one that are kept constant. All right. They don't change. When I say constant, I mean they don't change. In one situation and the other situation, all the temperature and the pressure are the same. That's what it means. All right. So Avogadro's law says that equal volumes of different gases at the same temperature and pressure can contain the same number of particles. So if you have maybe nitrogen, and then you have maybe oxygen, and then they have the same temperature and pressure, and they have the same volume, they will contain the same number of particles. Right? They will contain the same number of particles. So then, because the number of particles is related to the number of moles, one mole is equal to 6.002 times 10 to the power of 3 particles. This is Avogadro's number. Avogadro's number is 6.02 times 10
So
to
we
the
can't see
power.
your screen.
You can see the screen. I think I'm sharing it though.
No.
Yes, yeah, it's good. The screen is visible. Charlie,
Eh,
maybe check your side. Check your side where the screen is showing.
yes, I'm sharing because once I see as green, then it's sharing. The number of particles,
Okay, so I can see it.
yeah, the number of particles and then the number of volume are kept constant. I mean, the number of particles goes with the number of volume. They are directly proportional, right? V1 over N1 equals to V2 over N2. All right, V1 over N1 equals to V2 over N2. These are related, directly proportional, all right? A constant pressure and constant temperature. That's what he's saying. So if I give you carbon dioxide, or I'll give you maybe helium, I'll give you say neon. No, these are gases, all right? And then the temperature and pressure are the same, all right? And then if this contains maybe 2 liters, right? The number of particles that in neon will be the same, when I have 2 liters of what? Of and the same helium, all right? So that's how Avogadro's law says. The pressure and the temperature have remained constant. All right, so V1 over N1 equals to V2 over N2. So see the differences. Avogadro's law, Gay-Lussac's law, Boyle's law, and Charles' law. These are the 4 laws that are governing, these ideal gases that we have learned so far. Boyle's law first, Charles' law first, Gay-Lussac's law third, Avogadro's law. Like I said before, you have to know which one, when they give you this one is constant, everyone constant, which law we are going to use to do the problem. All right. So let's use this as an example and learn. A 2.45-liter volume of a gas containing 4.5 times 10 to the power 21 gas particles. How many gas particles are there in 3.87 liters? If the gas is at constant pressure and temperature. All right. Now, you've been told explicitly that the gas is at constant pressure and temperature. And now you have volumes. You have one volume, you have another volume, you have gas particles. So now it gives you a clue that which law you are going to use. You see that, oh, okay. You know what? Let me leave this for you to solve it and let's see how it goes. Let me give you some time to see, tell how many particles are there. When you finish, you can give me the answer.
Sir, so
Yeah, Philip.
the answer is 3.887.
3 point.
3.87 liters.
Philip said again, I didn't hear you. Philip, I
Three
didn't hear
point
you.
3.87.
Liters.
Yeah, liters.
Who else? Somebody, everybody agree with Philip, sir, because I'm going to show you the answer. Yeah, Pat.
Okay, sir.
Pat.
So,
Pat.
Yeah, so
sir,
the answer is Philip.
sir, so
Okay, so
the fundamental equation is the V1 over N1 and V2 over is equal to V2 over N2.
Exactly, you are right.
So if you want one, you just do change of subject.
Exactly.
Oh, okay, okay.
exactly.
I think Pat wanted to also come in. Patrick,
So I got 7.1.
you have 7.1.
7 point. Yes,
Okay,
sir.
I think the rest of your classmates are also trying because the answer that Flip gave to us was not okay. So I think he's doing it again. So let's give him maybe 2 minutes, 3 minutes. Let them also try and let's.
7.1 by 10.
You see, the Avogadro's law, right, says that when you have the same volume, equal volumes, right, and then the pressure and temperature are kept constant, then you will have the same number of particles. So I think that's the reason why Flip was saying that it will be 3.87. But here
Yes, yes, sir.
but the volumes are not the same. But Philip, look at the volumes. This one is 2.45, this one is 3.87. The volumes are not the same. So if the volumes are the same, then you could have gotten 4.5 times 10 to the power of 21 particles, right? If they give you the same particles, like first situation has 4.5 times 10 to the power 21 gas particles, and another instance is 4.5 times 10 to the power 21 particles, right? And then you have V1, which is 2.45. Then V2 will also be 2.45. When pressure and temperature are kept constant. You get it? So those are the laws. So learn the laws very well so that you apply it when it's needed. All right. But then the volumes are different. So you know definitely that the particles will be different. All right. Even though the pressure and the temperature are kept constant, then the volumes, you know, the particles will be different. All right. So if Philip has also finished or the rest of classmates have finished, then let's see, the answer. And I think Patrick was right. Patrick, is that what you said? 7.1 times 10 to the power 21.
Yes, sir.
Yeah, so Pat was right. Um, so our N2 is 7.1 times 10 to the power 21 particles. All right. Let's do more of this. Now we have a combined ideal gas law. The gas laws, we combine it. All right, P1 over P1 V1 over T1 equals to P2 over P2 V2 over T2. And then the number of moles are kept constant. You see, all these problems that we're doing, all the moles are kept constant, except the Avogadro's law, where the moles are not kept constant. The rest of them, all the moles are kept constant. All the laws that we've learned so far. It's only Avogadro's law that the number of moles are not kept constant. The rest of them, all the number of moles are kept constant. This one, the combined ideal gas law, V1, P1, V1 over T1 equals to P2, V2 over T2. The moles is constant. All right. This is combined ideal gas. But there are some situations that you'll be asked a question and then you need to use the combined ideal gas law to solve the problem. All right. P1 V1 over T1 equals to P2 V2 over T2. All right. So let's solve this and see how it's applied. All right. Or maybe I should leave it for you guys to try. Yeah, try your hands on. See, sometimes I know you do homework, but I make you try your hands on when we are in class so that it will be easy for us to really see where our shortcomings are. So try your hands on this one. Let's see how it goes. All right. A sample of gas at the initial volume of 8.33 liters. Initial pressure of 1.82 atmosphere. Initial temperature of 286 Kelvin. Then the changes, simultaneously changes its temperature to 355 Kelvin and its volume to 5.72 liters. What is the final pressure of the gas? What is the final pressure of the gas? So you try to see all the equation. When you are confronted with such a problem, right? You write the knowns, what you know, all right? The initial stage and the final stage. This is the initial stage. This is the final stage. So if this one is my initial stage and this is my final stage, then what do I have and what do I have on the final stage? What do I have on the initial stage? Then you ask yourself, okay, what is missing? If this is what is missing, what they are asking me, then which equation can I use to really solve this problem? All right, it becomes obvious once you are able to take your time. You don't rush, and then you take your time and write them all small, 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 small. You see that, oh no, I can apply this equation. Because sometimes you try to apply different equation, it won't work for you. All right. You see that I have more information that I need. I have this more information that I need. Oh, okay. I think this equation can be perfect for me. Then you use that, and then you see that everything will come into place. All right. So try this one. Let's see. Everybody get to work. And let's see your understanding of so far all the laws that we've learned. Pat,
Yes, sir.
Pat, Pat, have you done?
Sir, please, I got 3.29.
3.29. Okay, write it down. Please, Pat get 3.29. Don't say, okay, Pat had 3.29, so it's 3.29. You should also try to do it. All right. Try your hands on it. You the worker, sometimes you don't even get time to do your homework anyway. So that's why. Some of the workers, they even, they'll copy from their friends, their homework, and then submit it. You get your 10 points though. But then when where exams comes, it becomes a problem. I spoke to the people of the ICD, all right, and I was told that you guys will do your exams separate from the main guys. Your class rep, Kingsley, asked me some time ago, and then I found out for you guys. So I wanted to give you the update. So your exams will be different from the one they are the regular guys. They are writing the exams now. So you guys will come to the campus to write the exams. For that one, it will be different subject of matter. We can discuss about it later on. You understand? But that's how your exams is going to be. You come to the campus and you write it. All right. So just keep note of that. So Pat has his answer. So as everybody finish, let's see the answer. All right, let's see the answer. Yeah, Pat is right. It's 3.29 atoms. P1 V1 divided by T1 equals to P2 V2 over T2. Now, and then you just change your subject, multiply and divide by the temperature and then the volume. You have P2 standing by itself. And then you do the cancellation, multiply and do divisions. And then you get your answer nicely, neatly done. Okay. If you didn't understand it, after class, don't wait, go over them. All right. And then we have this extension of ideal gas law, right? This one, the number of moles are not kept constant, right? So PV over NT is why we say constant. And that constant is called gas constant, right? R. PV over NT equals to R. PV over NT equals to R. So some situation, you see the other one, the one that you just did, the gas, right? The gas, the number of particles or the moles was kept constant. P1 V1 over T1 equals to P2 V2 over T2. The N is constant. For this part, the N is not constant. It will tell you that, oh, okay. So when you find out that the N is not constant, then you can use PV over NT, which is equal to R. So PV, then if you cross multiply both sides by NT, then you have PV equals to nRT. PV equals to nRT. PV equals to nRT. All right. This one, the number of moles is not kept constant. The number of moles is not kept constant. So different scenarios, different situations will tell you which equation you have to use. All right. The R is a PV over N T, which equals to the R. The R has different units. I keep stressing on it. So if you don't use the correct number, you get answer, but your answer will be wrong. Especially when your examination is a multiple choice, All right. So because right now what you're thinking about is how to pass your exams. All right. But then you also learn and how we're doing environmental studies yesterday. We also learn, so that we can use it in the future, right? When you go to the lab and then you are trying to find the pressure and all those things, you use it. But as it stands now, your exams will be coming. So you have to also think about how to pass and pass well. All right. So in this case, all right, the number you use, the number we use goes with the units. For example, you have a numerical value here, which is 0.08203 and 0.5. All right. The unit there is liter atmosphere per mole Kelvin. All right. But then when you use 62.36, it becomes liter torr per mole Kelvin, which is also equals to liters times millimeters of mercury, or 1 torr is also equals to 1 millimeter of mercury. All right. And all you see, the denominators are all the same. All the units is mole Kelvin, mole Kelvin, mole Kelvin, mole Kelvin. All right. So liter times torr divided by mole Kelvin equals to liter millimeter of mercury divided by mole Kelvin. That's when you use 62.36. But then when you use 8.314, right, it becomes joules per mole Kelvin. Liter times millimeters of mercury is joules. Liter atmosphere is joules, right? It's energy, all right? Liter atmosphere is energy, all right? So it becomes joules. So now I use 8.314, 8.314. Then we use joules per mole Kelvin. So it depends on the units in the problem that you are given, right? Depend on the units that are given to you in that problem is what will tell you which uh, R you have to use. I'm saying again, because I see some students making that mistake. You know, they won't look inside the problem and see the units that they have in the problem. You know, the one that they lack mostly is the, 0.08205, and then they'll put it bam, and they'll put it there, and then they use to solve the problem. Meanwhile, they haven't checked to see the units that is inside the problem that has been given to them. One of the biggest thing that mistakes that students do. All right. So whenever you are given a problem, please check the units that are inside the problem. That will inform you which uh, the R that you need to use. Okay, three of them so far. So ideal gas law does not require a change in the condition of a gas sample. It doesn't require a change in the condition of a gas sample. The ideal gas law implies that if you know any three of the physical properties of a gas, you can calculate the fourth property. All right. So now let's use this to do an example. We have a sample of gas. This is argon, right? It's 4.22 moles, and its pressure is 1.21 atmosphere, and its temperature is 34 degrees Celsius. What is this value? All right, get to work and let's see how you come up. Everybody try this problem. Let's see. So far, who is finished? Who is done?
Please, can I
Pat,
try?
are you done?
Yes, sir.
Pat, what did you
So
get?
the correct 87.8.
That's 0.8. Okay, what is the unit? Pat, what was the unit?
So I come again.
The unit of the volume. I'm talking about the unit, whether it's or centimeters, cubic centimeter, whether it's cubic meter, whether it's milliliters, whether it's liters. What was the unit that you had?
So it was meters.
Liters.
Yes, sir, liters.
Oh, okay. They are also very important. There are some situations that you've been given a problem, right? And then they give you in different what you call it units. Even if it's maybe three, they can say 3 liters, 3 cubic inches, cubic meters. They just try to test your knowledge in those things, those units, all right, together with the
Okay.
problem that you solve. All right. So you have to be very careful. All right. You may know
Oh,
the thing though, but if you are not careful, it also comes out based on the R that you use and also other units. All right. So be mindful of that. All right. Anybody else finish besides Pat? Philip, have you finished? Engineer,
Yes, sir.
have you finished?
Yeah, not yet. The one that the first one that I got is wrong. I was going through, so I just finished.
Oh, okay. All right. Anybody
sir,
else? Kingsley
please,
is
can I come in?
yeah, coming, Pat.
No, for your
Okay, so
Telegram,
I thought
and then
that
you will see
I thought the
emails
first
about
answer
all that.
was wrong. It was
Do you want me to come and
87.9
do you want me
liters.
to take boats right now and come and drive?
Somebody is in your background disturbing. Tell your family you are studying or your friends. But in fact, have you finished? Have you gotten there? All right, let's see the answer together. So we use the PV equals to nRT. Right? PV equals to nRT. You see, we have our atmosphere, we have volume, we have moles. So we use the R, which is 0.8 0.08205 liter atmosphere per mole Kelvin. Then we change that distance to absolute because there's a mole Kelvin here. We change it into Kelvin, right? By adding 273 to it. Some situation they will use 273.15. All right, by this one is approximate number to 273 from Celsius to Kelvin. All right, add it up to then Celsius, and then we just do the multiplication, change of subjects, and then we came up with 87.9 liters. So that's how it goes. If you are gotten 87.9 liters, you are right. Okay. Now let's talk partial pressure. partial pressure. So each gas in a container has its own pressure. The partial pressure of a gas, Pi, is the pressure that the individual gas in a mixture has. Right? So any gas, if you put 10 gases in a container, all of them will have their own partial pressures. If you put two, they will have their own partial pressures. If you put one, that one gas will have its own partial pressure, which is one pressure, because the only one pressure, only one gas, right? So if you really want to, know how much, you can find each one of them and then add them all together to give you the total pressure of the gases in there. So gases mix with each other. When they do so, they become a solution. That's a homogeneous solution, a homogeneous mixture. Each component in the gas phase can be treated separately. Listen, each component in the gas phase can be treated separately. All right. Each component of the mixture shares the same temperature and volume. The component in the mixture, they shares same temperature and volume. Gases expand to fill the volume of their container. Gases in the mixture continue to do that as well. All right. So when you have a gas in the container, each one can be treated differently. All right. Each of them can be treated, but they have the same volume. They have the same what? The same temperature. All right. They will have the same volume. They have the same what? Temperature. So we have this Dalton's law of partial pressure. It states that the total pressure of a gas mixture, P total, is equal to the sum of the partial pressure of the components, Pi. P total is equals P1 plus P2 plus P3, all the way. So if you want to know the total pressure of the gas in there is going to be P1 plus P2 plus P3, all the way to the end, all right, to the end. But they will be having the same temperature. You can't say T1 plus T2 plus T3, no. You can't say V1 plus V2 plus V3, no. Right? Because they'll be sharing the same bond, and the same temperature. All right. So let's use that to do a mixture of helium at 2.33 atmosphere and nitrogen at 0.77 atmosphere in a container. What is the total pressure in the container? All right. So we just have to add them together, and then that's it. All right. So I'll end here with this, right? And I'll try to do, I'll try to let us do moles, right? How we can move from one mole to another. All right. Next time, God willing, when we meet, I'll try to let us do thermochemistry. All right. Thermochemistry. And so today, let's do moles. I'm going to unshare this slides and then share another one. Let me share this one. Do some. All right. Let me take this from here. It is somewhere that I can see the screen. All right. Example 8.1, right? Mole to mole conversion. All right. That's sodium chloride, right? It forms in this reaction between sodium and chlorine. All right. So now we see that sodium and chlorine, and then the equation is balanced. All right, it's balanced. While there are two moles of 2 atoms of sodium And then when for the product, at the reactant side, and then we have also 2 atoms of sodium on the product side. Then when we come to chlorine, we have Cl2, we have to see 2 of them at the reactant side, and then we have 2 of them at the product side. All right, I'm talking about these 2. All right, so then we found sodium chloride. And the question is, how many moles of sodium chloride dissolve from the complete reaction of 3.4 moles of chlorine? Assume that there's more than enough sodium. All right. So if there's more than enough sodium, that means, we can form we'll be able to form, because if we don't have enough, they become the limiting reactant. All right. Become limiting. So you have to have more than necessary so that you can be able to, all of them can react. All right. So now you are given the number of moles of a reactant, which is chlorine, and asked to find the number of moles of product sodium chloride that will form if the reactant completely reacts. All right. So you are given 3.4 moles of chlorine. All right. And you are going to find moles of sodium chloride. All right. So the strategy is this: draw the solution map, beginning the moles of chlorine and using a stoichiometric conversion factor to calculate moles of sodium chloride. The conversion factor comes from the balanced chemical equation. So that's the reason why we have to learn how to balance equation. If you don't learn how to balance the equation, you cannot be able to get your correct answer. All right. So now this is the map. All right. This thing here disturbs me a bit. So let me put it somewhere at the corner here. So that, yeah, I've hidden it. All right. So moles of chlorine, right? And then moles of sodium chloride. So this is the map that you draw. All right. So 2 moles of sodium chloride gives you 1 mole of 1 mole of chlorine. How do you know it? Come to the balance equation here. 2 moles of sodium chloride gives you 1 mole of chlorine. All right. So this is the map. 2 moles of sodium chloride gives you 1 mole of chlorine. All right. So now this is a 1 mole of chlorine gives you 2 moles of sodium chloride from the balanced chemical equation. All right. Then solve the solution map to solve, follow the solution map to solve the problem. So we have 3 moles of chlorine, right? Then use the mole to mole ratio, right? 2 moles of sodium chloride divided by 1 mole of chlorine, which will give you 6.8 moles of sodium chloride. There's enough chlorine to produce 6.8 moles of sodium chloride. All right. So now check your answer. Are the units correct? That the answer makes physical sense? The answer has the correct units, moles. The answer is reasonable because the moles of chlorine makes 2. A mole of chlorine makes 2 moles of sodium chloride. All right. Now, when water forms hydrogen, when water forms when hydrogen gas reacts explosively with oxygen gas, according to the balance equation, right? So how many moles of water result from complete reaction of 24.6 moles of oxygen? Assume there is more than enough hydrogen. Everybody get to work. Everybody, I want you to get to work. All right, you to do this one. Let's see how you come up with the answer you come up with. All right. Everybody get to work. Engineer, are you there?
Yes, I'm there. I'm there.
Oh, okay. I didn't hear from Kingsley. Kingsley, in the beginning, he started to talk and then later on he vanished. Kingsley, are you there? Kingsley. Uh, Usually he gets lost just like that. Oh, well. Are you done? Who is finished? All right. So let's do question. Let's do some more and then we can. This one is mass to mass conversion. In photosynthesis, plants convert carbon dioxide and water into glucose. In photosynthesis, plants they convert carbon dioxide and water into glucose, C6H12O6, according to the reaction. This is the reaction, right? Carbon dioxide plus water, carbon dioxide gas plus water liquid. They gives you oxygen gas and then the glucose, which is aqueous. How many grams of glucose can be synthesized from 58.5 grams of carbon dioxide? Assume that there is more than enough water present to react with all of the carbon dioxide. Add carbon dioxide. That's what the plants are doing. That's why we get food to eat. Let's say we were talking about environment, a whole lot of stuff that those renewable energy, renewable resources, and then non-renewable resources. All the plants that are around us, we need to plant trees and other stuff. So when the plants, when they are giving us food, we plant trees, and they are giving us cassava, they are giving us plantain, they are giving us this. That's what they are doing. They convert carbon dioxide together with water at the presence of sunlight, all right, to give us glucose and then oxygen. Then we can get some air to breathe, good air to breathe. So that's why in our houses we try to plant or we plant trees around us so that we can get oxygen, good air to breathe. All right. And then we are giving 58.5 grams of carbon dioxide. All right, that's what we know, but we don't know the amount of water. But we see there's plenty water around, plenty of them around to be able to for the carbon dioxide to react. Otherwise, we cannot get if you don't. There's not enough water to react with the carbon dioxide. we may not get, all the glucose to be produced. All right. So there's enough. The problem is there's enough carbon dioxide. All right. Or there's enough water. There's enough water because we are giving the carbon dioxide. There's enough water available so that no matter how much carbon dioxide is there, we can get to produce the glucose. And so how much glucose are we going to produce, right? I mean, the plant to produce, all right? You are given the mass of carbon dioxide and asked to find the mass of glucose. That can form if the carbon dioxide completely reacts. So given 58.5 grams of carbon dioxide, all right, and then we are going to find the grams of glucose C6H12O6. Strategy. You need to strategize. So when you are going to solve problems, you need to strategize, like I said before. You understand? You have the mass, you use the solution map. You have the mass of A. Then you have to convert it into moles of A. Then once you get moles of A, that the moles of A will give you the moles of B. Then once you find the moles of B, then you go back and convert it into mass of B. Let's go over it again. I have the mass of A. You need to convert it into moles. Then when they are reacting, they react in moles, mole to moles, right? See here, this is the mole, 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 mole. So they are reacting in the moles, mole to mole ratios, all right? So once they react in the moles kind of term, you can't use mass to get the other one that you know. So you convert the one you have into moles. They use the mole to mole ratio, right? The mole to mole ratio to get whatever you want. And then once you've gotten the moles of the other one, then you also go ahead and convert it back convert it into mass. All right, so we'll do it. A is carbon dioxide, B is glucose. All right. The main conversion factor is the stoichiometric relationship between the moles of carbon dioxide and the moles of glucose. The conversion factor comes from the balance equation. This balance equation that we have up there. All right. The other conversion factors are the molar masses of carbon dioxide and glucose. All right. So now this is the strategy. 1 mole of carbon dioxide gives us 44.01 grams of carbon dioxide. All right. Carbon dioxide. Carbon is 12. Oxygen is what? Is 16. So 16 times 2. 16 times 2, how much do I get? How much do I get? 16 times
32.
2. Very good. 32. And then add 12 to it.
44.
32.
44.
44. Very good. So
No,
now we have
yes.
44. Yeah, so we have 44 grams of carbon dioxide. It's 1 mole of carbon dioxide. Right? See, carbon dioxide, 44 grams of carbon dioxide, a mole of carbon dioxide. Then we come again. So we are converting 1 mole of, let's see the glucose. Let's put them together. Right? So 1 mole of glucose gives us 6 moles of carbon dioxide. Right? 1 mole of glucose gives us 6 moles. How did we get it? 1 mole of glucose gives us 6 moles of carbon dioxide. Go back and see. You see, look at here. 1 mole of glucose, 6 moles of carbon dioxide. So that's why it's important to do the balance. If you don't balance the equation, you cannot do this problem. Around 1 mole of glucose, 6 moles of carbon dioxide. So that's why we are using here. So 1 mole of glucose give us 6 mole of carbon dioxide. All right. So now we come back and say, okay, what is the number of grams of glucose per 1 mole of glucose? All right. So look, we have carbon. Carbon is 12. So 12 times 6 give us what? 12 times 6. 6 times 12. 6, 12.
72.
Yeah,
72.
72.
Thank you, engineer. Thank you. So then add, hydrogen is 1, right? So it's 12 of them. So 72 plus 12 is how much?
84.
84. Very good.
84.
84. Very good. Now 16 times 6. 16 times 6.
96.
96. Add them to the 84 that you had.
Plus 96 plus
180.
180.
Yeah,
Very
180.
good. Very good, everyone. So it's 180, grams of glucose per 1 mole of glucose. You see how it goes, per 1 mole of glucose. All right. So once we have this mole to mole ratio, then we have solved the problem. We already solved the problem. So we convert the moles into the grams. I mean the grams into moles, and then the moles, we use the moles to mole ratio, and then we can use it to form the last means we get this moles, and this is so look, the moles will cancel moles, and then the grams will cancel the grams, and we have it the mole. All right. So now watch. 6 moles of carbon dioxide is 1 mole of, give us 1 mole of glucose from balanced chemical equation. The molar mass of carbon dioxide is 44.01 grams per mole, and the molar mass of glucose is 180 grams per mole. All right. So once you know those things, your solving those problems become easy for you. So you follow the solution map to solve the problem. Begin with grams of carbon dioxide and multiply it by the appropriate factor to arrive at grams of glucose. All right. So that's what we are doing. Look at how we are doing. This is the solution. 58.5 grams of carbon dioxide. We have 1 mole of carbon dioxide give us what? 44.01 grams of carbon dioxide. So the grams will cancel the grams. Right, then we have the moles. Then we use the mole to mole conversion factor, the mole to mole from the balance equation. All right, then we get the number of moles of it. All right, the number of moles of the glucose. Once you get in the number of moles of glucose, then we also use the molar mass of the glucose, which is 180.2 grams of glucose. Then we multiply by it, then we get our answer. We have 39.9 grams of glucose. Then we are done. We solve the problem. We are done. Okay. That's how. So for the first one that we did, we had the mass, right? We have the moles, mole to mole. And now we move a bit forward. We have the mass, then we convert it into moles, and then we have the moles. Then we use to mole ratio to get the moles that we have that for another one. Then we are we are using the molar masses, right? The molar masses of glucose and carbon dioxide. All right.
Why are you sleeping?
Then we use it to get our answer. So simple.
I call him.
Are you okay now? Philip, are you trying to talk? Or somebody's behind you? All right. So I think we'll close from here. All right. We'll close from here. I don't know. Philip, when is the exams coming up? Because Kingston is not there. When Kingston is not there, you are the one who take over.
It's 31st. Yeah, it's 31st May. The exam will start from 31st May.
31st May. Oh, okay. So then we have enough time to do more studies. All right. See you guys
Yeah.
next week. God bless. Have a nice weekend.
Thank you, sir. Same to you.